If I punch a wall, why does my hand hurt? Ouch. Well, I'll let you think about that for a little bit as we... Today we're talking about Newton's third law, and it is often called the action-reaction law. And basically what it says is forces occur in pairs. So there's an action force and a reaction force. So for example, if I'm this little guy here, actually I should make sure to put a little extra hair on there. There we go. That looks more like a Gaglardi. If I push on this box, I put a force on the box. That's this force right here, the action force. So there's a force here pushing the box forwards. The box pushes back on me with the exact same force. That's the reaction force. That's why as I push on something, that's why I feel it. That's why my hand is going to feel the box, because the box is putting that force back on me. So what Newton's law then says is this in words. It says for every action force, there's an equal but opposite reaction force. The equal part means equal in magnitude. So that means it's the same number. If the action force is, for example, I don't know, 10 newtons. Let's look at these guys on the chair. If this guy here puts a force on this guy here, maybe let's stick some letters here. If guy A puts a force onto guy B, if there's a force going this way well, let's say this, the force that A puts on B, if that is, I don't know, 25 newtons, then B actually is going to push on A with the exact same force. That's why when guy A pushes on guy B, guy A is actually going to roll backwards in his chair, and guy B is going to roll forwards, or guy B is going to go this way and guy A is going to go this way. They're going to go in opposite directions. And the reason for that is Newton's third law. The force, if A puts a force of 25 newtons on B, then B is going to put that exact same force on A. That's equal in magnitude, right? They're the same number. So that's this thing here, equal in magnitude. The opposite in direction, we're also showing that on here. One is to the right and one is to the left. Here's another example of it. So it's the same law, Newton's third law. Here's our guys with their chairs. Here's another scenario. If a man attaches a rope to the wall here, he pulls on the rope, and the scale in the middle here reads 500 newtons. Okay, so he pulls on the wall. This scale here measures how much force he's pulling with, or it measures the tension in the rope. If the same guy then detaches it from the wall and instead attaches it to an elephant and pulls on the rope with the same force that he was pulling before, so same force is up here, he's pulling down here. Again, they're not moving because he's not strong enough to pull this elephant. If they're not moving, now what does the scale read? The scale is again going to read 500 newtons. So here's the answer, 500 newtons. And you might say, well, wait a sec. If the guy pulls this way with 500 newtons, the elephant's got to be pulling this way with 500 newtons. Shouldn't the scale read 1,000 newtons? Or maybe 0. Sometimes people think, well, these forces maybe cancel out and there's 0. But let's think about what's going on in the first diagram. Usually the first diagram makes sense to people. He pulls with 500 newtons this way. The scale reads 500 newtons. What's going on over here, though? The reason the rope is not moving this way is because right here the wall is pulling back with 500 newtons. This is true by Newton's third law. If the wall wasn't pulling back with this 500 newtons, then the rope and everything is going to start to move this way. The reason it's not moving is because the wall is resisting with that 500 newtons. The elephant over here doing the exact same job that the wall was doing before. It doesn't matter if it's a wall or an elephant or a car or a person. They're all doing the same thing. They're all resisting with that same 500 newtons. So here's another common question. If the action and reaction forces are equal, then how is it that the object can move? I mean, shouldn't those forces cancel each other out? Shouldn't this action force over here cancel the reaction force? We put lines through them both and say, well, it's a balanced force situation. This thing is never going to move. And that's not true. That's not quite what's going on. And here's the answer. The forces don't cancel because the action-reaction forces are on two different objects. So that's really important. This thing right here, the action and reaction forces are on two different objects. So if we look down here below, we'll finish the sentence in a sec, but if we look down below and if we look over here at the box by itself and over here at the guy by himself, maybe we should stick that hair back on just to show who it is. If we look at the two objects by themselves, then we would say, well, this action force that we talked about up here is right here. That's on the box. This reaction force over here, that's over here. That's not on the box, that's on the guy. So if I look just at the box, let's go over here, look just at the box, we'd say, well, there's an action force of 50 newtons. If the box is going to move, then what I know is that that action force, at least at some point to get it going, must have been bigger than the force of friction. So maybe the force of, let's say static friction or something was 40 newtons. Now the box is going to move. It's going to accelerate forwards this way because this action force is bigger than the force of friction. So to get back to our question here, how is it that the object can move? As long as the action force is greater than the static friction, then the box is going to start to move and in fact accelerate off to the right. We could go back to the guy and say, well, what about the guy? He's got this reaction force of 50 newtons pushing him backwards. How is it that he could move forwards and walk with the box? Well, same idea. He needs some force to be bigger than this reaction force in order for him to accelerate forwards this way, or to go forwards. So the force for him, and you might say this is a little bit of a confusing one, but you might say, well, he's gonna push backwards on the floor with his leg. By Newton's third law, as long as his shoes aren't slipping, there's this force of friction that prevents his shoe from slipping, and so it's actually friction that pushes him forwards. Friction, we've talked about how friction always opposes motion. The motion that friction here is opposing is his shoes sliding backwards on the floor. It's keeping it rooted in place. So he's using his legs, but it's actually friction that pushes him forwards. That's a bit of a confusing one. You can ask me that one in class. So we'd sit here, as long as the applied force then on the box is bigger than friction, then this object can move forwards. And in fact, it's going to accelerate. These are unbalanced forces, so it's going to accelerate forwards. Okay, so here we've got two boxes being pushed forwards by a force of 80 newtons. So the guy here is pushing forwards with a force of 80 newtons. We've got friction resisting, so this box slides on the ground, and so does this box. I don't know why my boxes go below the ground here. When I look at it on the computer, they don't, and when I bring it onto this tablet to do this video, for some reason my boxes go down here, so let's ignore the boxes going down here. Forget this part. The boxes end here on the ground. As this guy pushes the boxes forwards, I'm going to look at this. I want to draw a free body diagram. I'm going to look at this as a system. So let's say this. Here is the system. You could say it's a system free body diagram. Let's say that. As the guy pushes the boxes forwards, this is just the boxes. So I'm going to picture, here's kind of the two boxes together as a system. They're resting on the ground. They're going to have a combined force of gravity pushing them down. They're going to have a normal force going up. This normal force is equal to the force of gravity. We don't need to consider those balanced forces. We're just going to look at the unbalanced forces. For the unbalanced forces, well, the guy, we're told, is pushing this way. So there's an applied force, what does it say, 80 newtons? There's an applied force of 80 newtons forwards. Then up here it mentions that there's these two forces of friction. So there's a friction from box A. We could consider them separately, or we could add them and consider them together. I'll just show them separately here, just so we can see them both. There's a friction from box A, back this way. And just to really be colorful here, I'll show you a second color. Let's say the friction from block B, what is that, 7 newtons? There's a 7 there, 7 newtons. Okay, so there's two frictions, they're going back this way. When I look at this thing, there's my free body diagram. I want to start by saying, okay, sum of forces equals ma. And remember, when we say sum of forces, it's the unbalanced forces. So Fn and Fg are balanced, they cancel out. What I'm left with then, my unbalanced forces, are the applied force and I always seem to do this, I should say what my positive direction is going to be here. I'll stick with up as positive, and in the direction of the applied force, we'll make that positive. This isn't turning into a nice arrow, but this way is positive. So my applied force here, it's in the positive direction. Both of my friction forces are in the negative direction. So here we could say negative, let's put a little negative there, negative FFA and plus negative FFB is equal to MA, M total times A. The reason I'm saying M total is because it's a system free body diagram. Whatever object or objects I'm looking at, that's the mass that goes in here. So this, what I'm looking at up here, dictates what mass is going to go in there. It also dictates what forces are acting on it. So the applied force, we know what that is. That's just 80 newtons. It's in the positive direction. Friction, remember friction was negative because it's in the negative direction, so that's 5 newtons. Friction B, that's 7 newtons, again in the negative direction, that's why it's negative. The two masses, let's see, we've got a 20 kilograms and a 30 kilograms, so I'll write it as that. I'll say 20 plus 30. You can do that in your head, that's just 50, but just to show you where these things are coming from. Oops, I don't know how that line got on there. Always making these crazy extra lines. And this was force of friction here. Negative friction, there we go. Okay, so this is negative 7 newtons here. When I go ahead, oh yeah, and I've still got acceleration, I almost forgot. Got distracted by my straight line. Acceleration is still there, that's what I'm going to try to find. If I do 80 minus 5 minus 7, that is, let's see, 68. 20 plus 30, that's 50. A. We can divide that and we can say acceleration is 1.36 meters per second squared. That's to the right. And for significant digits, we could round that to 1.4, which I suppose we should say. I'll see if I can squeeze that on the bottom. Acceleration, 1.4 meters per second squared to the right. And here's my answer. There we go. The second part of the question asks for the force that A exerts on B. So let's see if we can squeeze that over here. This was part A. This over here then is part B. What force does A exert on B? If we're looking for stuff on B, I'm going to look at block B. Okay, so instead of a system free body diagram, I'm going to do a free body diagram just for block B. Okay, block B on its own. My starting point is always the same. This is just Newton's second law, F equals ma. But if I look at block B by itself, let's see if we can just do a little free body diagram for block B. Here's block B by itself. The guy's applied force, remember this 80 newtons of applied force, that does not act on block B, that acts on block A, right? Over here he's pushing on block A. So something pushes block B forwards. And that's actually the thing that I'm looking for. It's the force that A exerts on B. So here I can say force that A exerts on B. That's what makes block B go forwards. There's of course some gravity and normal. And as usually happens, at least in grade 11 physics, those forces cancel. Then there's this friction force going back. And remember over here we said there was 2 friction forces because we were looking at the system. If we're looking just at block B, then I only have the 1 friction force. So let's see, it said there was 5 newtons on block A. Here, there's 7 newtons on block B. That's my friction. Okay, so friction is just 7 newtons, not the full 12 newtons this time. So now when I say sum of F, remember sum of F is all the unbalanced forces. So again, normal and gravity cancel. What I'm left with is A on B, pushing to the right, that's my positive direction. And I've got friction, just friction from block B this time. And like we said before, the mass that's in here is dictated by whatever object I'm looking at. This is just mass B, that says mass B there, times acceleration. I don't know the force of A on B, so I'm just going to leave that as A on B. I do know friction. That was 7 newtons. That's a 7 there. Mass B. Mass B is 30 kilograms. That was from up here. And acceleration, that's whatever we had back in part A. So this acceleration over here is going to come up in here. I'm going to use my unrounded value, 1.36. That's a 6. Now I can go ahead and work some stuff out here. Let's see, this is 30 times 1.36 is 40.8. FAB minus 7. We're going to take this minus 7 to the other side, so FAB is, to be there, 40.8 plus 7. So the force that A exerts on B is 47.8 newtons. That's approximately 48 newtons. We'll do our rounding for significant digits here. It's approximately 48 newtons. That's in the forwards direction, my positive direction. And there is the answer. There's what force, that's the force that box A exerts on box B. Lastly, for part C, we could go and we could do a whole new free body diagram for object A. And in class we may do that just to compare, just to see it. But by Newton's third law, if box A exerts a force of 48 newtons on box B, then box B has to exert the exact same force. Remember we said it's equal in magnitude but opposite in direction. This thing here, exact same force, so there's the equal in magnitude but opposite in direction. If this one is forwards, this one is backwards, or you could say one is to the right, one is to the left. And by Newton's third law, I can answer this part. The force that B exerts on A is same thing, 48 newtons, but backwards. So lastly, if I punch a wall, why does my hand hurt? Because of that crazy Newton. Newton's third law is for every action force, there's an equal but opposite reaction force. If I punch a wall with a force of 500 newtons, the wall actually punches my hand back with a force of 500 newtons, and that hurts. Ouch.